Can somebody please confirm you can hear me?
I can hear you.
Thank you. All right, before we begin, are there any questions? Close that down. I just got an email. All right, today is January 15th, and we are supposed to be already started on chapter 2. We're a little bit behind schedule. We need to finish up chapter 1. There will be a lab today. Any questions about what we're going to be doing? And remember, I'm here to help you, so if you have any questions, just let me know. Oh, wrong one, sorry. All right, I have that we had talked about Alexander Fleming discovering penicillin, the first antibiotic to be discovered, not the first antibiotic to be clinically available. That was actually a sulfa drug, sulfonamide. When we're talking about microbes and human disease, you should realize that once bacteria were classified as plants, hence the term microflora. And unfortunately, I learned the term microflora when I took microbiology. That was, of course, many years ago, but when I was an undergraduate, they used the term microflora. They don't use that term any now. It's used replaced by microbiota because, as you know, um, well, microbes are not plants, and so we shouldn't be using the term flora for microbes. Any question about that? The normal microbiota are the microbes present in and on, well, we're talking about humans. The normal human microbiota is on humans. There are different uh, microbes on animals, like, say, your cat or your dog. They do have many of the same microbes as we have, but they have some that are different. And I just know one on cats, which is the normal microbiota of cats, is Bartonella henselae, which does not cause any disease to cats. But to people, Bartonella henselae causes a disease we call cat scratch fever. So the normal microbiota are different on each organism. They can even be slightly different on different people. As you know, some people have Staphylococcus aureus as part of their normal microbiota for their skin. About 20% of Americans. The majority of Americans, about 80% of us, do not. And Staphylococcus aureus can cause skin diseases. So, that's just something some people have to live with. Usually it's just a boil or something like that, but it can be, once it gets into the blood, it can be a serious disease. Anyways, animals and plants are host to symbiotic microbial communities, the normal microbiota of the animals and plants, and they are actually central to their welfare. The normal microbiota of humans, for example, helps us digest our food. It makes certain vitamins for us, like vitamin B12 and something else I don't remember. Let's see if I have it here. Folic acid and vitamin K. There it is, vitamin K. That's the one I was forgetting. Folic acid is B12. But the normal microbiota is usually found on or in the skin, the oral and nasal cavities, the respiratory tract, the digestive tract, and the urethra. The normal microbiota is not usually found in the blood, in internal organs, or internal tissues. The normal microbiota is actually important to, well, humans, when we're talking about human normal microbiota, because the normal microbiota can prevent the growth of various pathogens. They can compete for resources or simply for the space. For example, I've got a lot of normal microbiota on my skin here. Hopefully you can see that. And if I were to get a Staphylococcus aureus coming down and falling on my skin, well, it might not get established because it'll fall on top of where some of my normal microbiota is. And then if it falls even nearby, it can compete for resources and not get enough resources to get established. The normal microbiota can actually secrete toxins that inhibit the growth of certain pathogens. The normal microbiota do produce nutrients and growth factors for people, like folic acid, vitamin K. They help with our digestion. We'll talk a little bit about the toxins, like E. coli in our gut can produce a toxin that will prevent salmonella and Shigella from getting established in the gut. Any question about any of that? The normal microbiota can also change the environment, making it inhospitable to a pathogen. And one example is the microbes on our skin make the skin more acidic. The microbes in our mouth also make it more acidic, preventing the growth of certain pathogens. Any question about that? All right. The normal microbiota do not normally cause disease in a healthy patient. However, they can cause disease in certain circumstances, such as when a patient has no immune system. And we'll talk a little bit more about that in the normal case. When the normal microbiota do cause disease, it's usually called an opportunistic disease because the normal microbiota does not normally cause disease, at least in a healthy patient. But if your immune system is failed, like you have advanced AIDS or you have chemotherapy for some, you're taking some drug for cancer or something like that, the normal microbiota can cause disease. Infectious disease results when a pathogen overcomes the host resistance, and infectious diseases are caused by a pathogenic microbe. Remember, only a few microbes are pathogenic, meaning only a slim percentage of all microbes are pathogenic. An emerging infectious disease is a new or changing disease that is either increasing or has the potential to increase in incidence. Can anyone mention an emerging infectious disease?
COVID?
COVID-19 is still considered an emerging infectious disease because it first came out in 2019, which now is, I guess, almost 6 years ago. But no, I guess it is 6 years ago now. Well, we'll be in December, I guess. No,
It's 6 years,
yeah, it's
2026
six
now.
years ago. I don't know when it switches becoming a emerging infectious disease and then a normal infectious disease. COVID-19 has become part of the human normal microbiota. It does cause disease, but it looks like it's going to be a bug that's going to be with us for, well, in foreseeable future at least. So, but it is still considered an emerging infectious disease because it first came out in 2019. Another emerging infectious disease, one that they're worried can increase in incidence, is bird flu. At the moment, when bird flu hits a human, it doesn't spread human to human because bird flu needs to um, spread fecal to oral, and so it doesn't really spread, at least very quickly, among humans. But the concern is it could spread human to human, and then we'd have another lethal viral disease spreading. Bird flu is viral, if you don't know. So you need to know the definition of emerging infectious disease. But beyond that, I'm not going to talk about emerging infectious diseases. You can read about it here. I'm not going to quiz you on it other than that it is a new or changing disease, one that is either increasing in incidence or has the potential to increase. Can be any microbe. Any question about emerging infectious diseases? All right. That's it for chapter 1. Let's go on to chapter 2. Chapter 2, Chemical Principles. The major goals in a rough outline are showed here in this slide. Know the terms. What's an organic compound? What's an inorganic compound? What are hydrocarbons? What are polar and nonpolar molecules? What are hydrogen bonds? What's an acid, a base, and what is the pH? Also, to be with respect to the 4 major biological molecules, be able to describe the relationships and characteristics between the monomers and the polymers. What are the 4 major biological molecules? You can find 3 of them on any cereal box or any really food wrapper. Anyone know what some of the 4 major biological molecules are?
Are we talking about like carbon, oxygen, nitrogen, hydrogen?
No, those aren't molecules. Those are actually
Carbohydrates.
elements. Those are atoms.
Got
Carbohydrates.
excited.
I'm sorry?
Carbohydrates.
Yeah, carbohydrates, lipids,
Protein.
proteins, and then the
Yeah.
4th, which you don't find on any cereal box, would be nucleic acids. Did somebody give me a message? Let me stop my share here and take a look. Something came up on my screen. Yeah, when you give a chat, I'm not going to be able to see it. So you shouldn't use the chat because when I'm sharing my screen, I don't really get to see what you stated. But you're right, proteins and lipids are some. But you need to, how do I get out of here now? Share my screen again, I think. There we go. So when you give a chat message, I don't see it. I saw something briefly happen, and so I guessed it was a chat, but you shouldn't use the chat because when I'm sharing my screen, I can't see it. So the 4 major biological molecules again are carbohydrates, lipids, which we normally call fats, but it's a few more than just fats. So we'll call it lipids, and nucleic acids. I'm missing one. Protein. There it is. There are the 4. You find these molecules only around living organisms. And if they aren't in something that is alive, they were made by something alive and then secreted, or there was something once alive. Like you find it on a fossil on the planet Earth, it's because the fossil, when it was alive, made the 4 major biological molecules. You never find these molecules on a rock from the moon or a rock from Mars because there's no life on the moon or Mars. Anyways, with the 4 major biological molecule, be able to describe the composition, the structure, and the function, and be able to give examples of each. In chapter 2, you need to know the scale of things. Let's see if we can blow this up. So you should know the largest thing we're going to be studying really is about a human. You could say a whale or elephant or larger, but um, an organism, a big organism like a human. The next largest thing we're going to discuss would be something like an egg, chicken egg, which actually the yolk of the chicken egg is the largest cell you guys have probably ever seen. I once had a student who saw the yolk of a turkey egg, but they're kind of hard to come by, so most people haven't seen that. I've never seen the yolk of a turkey egg. There's a frog egg. That's about the smallest thing you can see with your human eyes. Anything smaller, you kind of need a microscope. That includes a eukaryote cell, a bacteria, which is even smaller, viruses, which are even smaller, large molecules like proteins, are smaller than a virus. And then you have small molecules like water, which are smaller than proteins, lipids. And then the smallest thing, let me get that out of the way. Oop, sorry. Let me go back. Come on. The smallest thing we're going to talk about is atoms. There are things smaller than an atom, but we're not going to talk about them in this class. An element like iron or oxygen, the smallest thing you can have of that element would be an atom. Any question about any of that? Now realize there's actually a mistake in this graph, and for some reason Pearson has never updated it, and that is they have 1 micrometer there and 1 micrometer there. That one right there should be a milliliter. All right, what are organic compounds? Typically, organic compounds are complex compared to inorganic compounds. They also typically have carbon in the organic compound. In fact, all organic compounds have carbon and hydrogen. But carbon is important because carbon can bind to 4 other atoms. And carbon, the carbon-carbon bonds, tend to hold most of the atoms in the organic molecule together. I'll show you what I'm talking about in just a minute. Inorganic compounds typically lack carbon, not always, but they typically do lack carbon. They are required by living organisms for their organism's growth, repair, and maintenance, and reproduction. Some examples of an inorganic compound include water, oxygen, and carbon dioxide. If you note, carbon dioxide does contain carbon, so an inorganic compound can contain carbon, but they don't typically do. Water is one of the most important and abundant molecules in living organisms. You're something like 70% water, and that's true for almost all living organisms. Any question about any of that? All right, let's talk a little bit more about water. Water is a molecule made up of 2 hydrogens and oxygen, and they have a chemical covalent bond holding the atoms together. The chemical covalent bond is held in place by 2 electrons that form the chemical bond. We're not going to talk about that. It should have been something you covered in your previous class. Water is a polar molecule. What do we mean by a polar molecule? A polar molecule is one that has a partial positive end and a partial negative end. Oxygen pulls on the electrons in this covalent bond holding the hydrogen and the oxygen together. And so the electrons spend more time around oxygen than they do around hydrogen. This makes oxygen partially negative and hydrogen partially positive. Now, Totora doesn't call it a partial charge, he calls it a slight charge. I prefer the term partial charge because it makes it clear that it's not a -1 around the oxygen and a +1, meaning a complete +1 charge on the hydrogen. It's a partial charge, some fraction less than 1. Any question about any of that? The polarity of water allows water to form hydrogen bonds with other molecules, including with water. For example, let me blow this slide up. Here is a water molecule here, and we have oxygen, a partial negative charge, and hydrogen, a partial positive charge. This is an electromagnetic attraction between that partially negative oxygen and the partially positive hydrogen. That electromagnetic attraction forms the hydrogen bond. In liquid water, the water hydrogen bond tends to break all the time. And that is why, I don't know if you can see this, maybe it's T, so maybe you can see that. But that's why water is a liquid, because the hydrogen bonds are breaking and reforming all the time. And that's why the liquid, which you can sort of see, takes on the shape of the container, because the hydrogen bonds break and reform all the time. You can make it where this hydrogen bond forms and never breaks. That's not liquid water. What is it? Where this hydrogen bond never breaks. It's not liquid water, so what is it? Come on, somebody's got to know. You got to guess. If it's not liquid water, it has to be one of two other states.
Ice?
Yeah, it's ice. Solid water we call ice. And with solid water, the water molecules themselves are moving so slowly that they do not have enough energy to break the hydrogen bond, sorry. And so that hydrogen bond stays in place and the liquid water becomes a solid and it does not change its shape. And that's why we call it a solid, because the hydrogen bond is permanent and it locks the water molecules in place, keeping the water from changing its shape. In liquid water, the hydrogen bond breaks, and so the liquid water can take the shape of the container, whatever the container shape is. And that hydrogen bond breaks and reforms all the time. You can find polar molecules in water, in sugars, in other polar molecules. Now remember, water has two chemical bonds. It has a hydrogen bond inside the water molecule, excuse me, not a hydrogen bond, a chemical covalent bond between the hydrogen and the oxygen inside the water molecule. And then it has a hydrogen bond between different water molecules. As long as the water is liquid or ice, it'll have a hydrogen bond. Now, if you have water vapor, the water molecules have so much energy that all of the hydrogen bonds break, and then we no longer have liquid water. We have water vapor or gaseous water. Any question about any of that? All right, you can watch the little video. It's not terribly great on water, so let's move on. Water is a good solvent. All polar molecules and ions dissolve in water. An example is sodium chloride, which is actually an ionic compound formed between a negative 1 chloride ion. It has a complete -1 charge, and then a complete +1 sodium ion. And then this would be a salt crystal. So you dump out your salt, you can see the crystal. And it actually is simply chloride being a -1 being attracted to the +1 sodium. And then it forms this crystal, which would be the salt crystal you're looking at. And you put that one crystal in water, the water will come around well, let's make it the green one here, the +1 sodium, and then the water will orient so the negative, partially negative oxygen will face the +1 sodium ion, and then the water will come in, surround that, and then pull it into solution. And the same with the -1 chloride ion. The water will come around it, and the hydrogen, partial positive hydrogen, will orient towards the -1 chloride ion. It'll surround the chloride ion and then pull it out of the crystal, pulling it into solution. And eventually this crystal will dissolve as the water comes around and pulls it out. And then we won't have any solid salt crystals in the water. It'll only be sodium chloride solution having salt in the container here. Any questions about any of that? All right, somebody is ringing my doorbell. Can you guys hold on just for a second? I want to see who is at my door. and I'll be 1 minute. Sorry about that. Everyone back?
Was it
You
anything exciting? Amazon package?
No, it was actually some Mormon missionaries.
Oh,
you
they'll
said
get you.
that you
Huh?
said that we could look watch these videos later in the PowerPoint. Uh so are we so do we get the links from your YouTube channel by rewatching this lecture? Or
You
do you
could do it that way. Another way to do it is to just go to my YouTube website and let me show you. We won't have it for lecture 2 yet, but let me go to lecture 1. I forgot to do this when I actually shut it. When we're done with the lesson, I'm going to now publish my notes. So lecture 1, the notes are actually up. You might be able to find the link in the study guide. I don't know if it's there or not, but it's definitely here. Okay. So when we finish chapter 2, I will publish the notes. And if it's not published a day after I finish chapter 2, you just send me an email as a reminder. Okay.
Okay, thank
But
you.
yeah, if you wanted to see it right away, you'd probably have to look it up on my YouTube website. All right, let's go back to the lesson here. And sometimes I do play the videos, like I'm going to play this one here, if I can get it to open. Yeah. Ah, where is it? Ah, did it open? No, no. For some reason I couldn't get that to open, so I'm just doing it the hard way. So there's a water molecule. There's a sodium chloride crystal, a bunch of water molecules, and there's a hydrogen bond between the water molecules. Partial positive, partial negative charge. Chloride, +1 and -1 for the chloride ion. Salt crystal here. And there's water molecules coming in. The hydrogen's coming around the -1 chloride, pulling it out. The oxygen's coming around the chloride, +1 chloride, and pulling it out. Any questions about any of that? And then there's a chloride ion in the water, being surrounded by water. And then a whole bunch of water molecules coming in, pulling the ions out of the salt crystal. Any questions about any of that? Eventually, the salt crystal will dissolve, and you'll have all the sodium chloride in the water, making it salt water. All right. Water is a good solvent, and that is polar molecules are hydrophilic. Hydrophilic means literally water, hydro, and then philic, lover. So they're water lovers. What it really means, obviously, it does like to be around water, but hydrophilic or polar molecules mean that they dissolve in water. They like being around water. Nonpolar molecules are repelled by water, and they are hydrophobic. Literally, this means fear of water or water fear. So fear of water. They do not dissolve in water. So a nonpolar molecule does not dissolve in water. An example of that would be a fat like butter or oil. And as you know, if you've all made salad dressing and put vinegar and oil together, the vinegar is mostly water and it will separate from the oil. And that's because the oil is nonpolar and the vinegar and the water are polar. Any question about any of that? See if this one's good or not. Oh, that one opened.
Monday.com, the opposite of any work platform we tried in the past.
Yeah,
We
that's a
tried other work
commercial,
management
sorry.
platforms, not naming names.
Skip it. Water.
Life, as we know it, would not exist without water. Over 70% of the planet is covered in water, and our bodies are around 70% water. But why is water so important? The structure of a water molecule and the fact that it is capable of forming hydrogen bonds with multiple other water molecules simultaneously provides water molecules with some very unique characteristics. These include the ability to act as a universal solvent, the properties of cohesion and adhesion, a high surface tension, a high heat capacity, and changes in density based on temperature. Let's take a look at each of these in turn. Water is often called the universal solvent, which means that many substances dissolve in it. Water's solvency has to do with the polarity and hydrogen bonding ability of water molecules. When a salt, such as sodium chloride, is placed in water, the negative ends of the water molecules are attracted to the positively charged sodium ions, and the positive ends of the water molecules are attracted to the negatively charged chloride ions. This attraction causes the sodium and chloride ions to break up or dissociate in water. Why is this important? Since our cells are mostly water, these solutions of ions and molecules allow chemical reactions to occur much more frequently, which is an important feature to allow organisms to respond to their environment. Water molecules are also cohesive and adhesive. The hydrogen bonds in water cause water molecules to stick together, a property known as cohesion. Polar bonds also give molecules an adhesive property, or the ability to cling to other polar surfaces. Why is this important? Well, water fills the internal transport systems of plants and animals. Because of these cohesive and adhesive properties, water allows for the efficient transport of nutrients and waste within an organism. Water also has a high level of surface tension. Because water molecules at the surface are more strongly attracted to each other than to the air above, water molecules cling tightly to each other. The surface tension of water explains why it beads up on waxy surfaces and why water-striding insects are able to walk on the surface of water. Water has a high capacity for heat. What this means is that the many hydrogen bonds that link water molecules let water absorb a large amount of heat without changing its chemical state, for example, from liquid to gas. This not only stabilizes the temperature of bodies of water, such as lakes and oceans, but also plays an important role in the physiology of an organism. Since life is based on water, and the temperature of water rises and falls slowly, living organisms are better able to maintain their normal internal temperatures and are protected from rapid temperature changes. And finally, the density of water is based on its temperature. Unlike many other compounds which contract when they freeze, the configuration of the hydrogen bonds in water causes it to expand when it freezes. This expansion causes ice to have a lower density than liquid water, and therefore ice floats on liquid water. If ice were more dense than water, it would sink, and ponds and lakes would freeze solid, making life there impossible. Instead, bodies of water always freeze from the top down. The ice on the surface acts as an insulator to protect the water below from freezing. This protects organisms so they can survive the winter.
All right, any questions
How
about
people in
that
the
video?
1920s
All right, let's talk a little bit about the properties of water. Hydrogen bonds between water molecules makes water excellent at buffering the temperature. I think you guys might all know this because in Western Washington and Western Oregon, our temperature is buffered compared to the eastern parts of the states. Water absorbs a lot of energy, meaning heat, before it becomes heated or evaporates. It takes energy to break the hydrogen bonds, and also water absorbs energy to vibrate the water molecules. When you're talking about any thing's temperature, you're talking about how fast the molecules are moving. Something that has molecules moving around quickly is something at a higher temperature than something where the molecules are moving around slowly. So when we're talking about, I don't know, solid ice, the water molecules are not moving around very much because the temperature is low. And then gaseous water, the water molecules are moving around quickly because the temperature is hotter. And that's true of any substance, like you're talking about, I don't know, the metal of this glass, or maybe the spoon would be better. And if you freeze it, the molecules of the metal are not moving around very much, and that's why the temperature is low. And then when you heat it, the molecules will start moving around faster, and the temperature will be elevated. And so the temperature is just the amount the molecules are moving around. If you heat this really, really high and make it liquid, the molecules will be moving around, and you heat it even further, all the molecules will be gaseous, and the molecules are moving around even further. Any question about that? So that is all temperature is. With water, you give water energy. Some of that energy will be absorbed by the molecules, so the molecules will move around faster. That will elevate the temperature of the water. And that happens with all substances. When you add energy to the substance, the molecules will move more rapidly and the temperature will elevate. But when you add energy to water, there's something else that can absorb that energy, and that is the hydrogen bonds. If you absorb the energy by the hydrogen bonds, then the temperature of water will not increase. And so there are two things in water that can absorb the energy. And that's why water is excellent at buffering the temperature. Like if you had a container of oil here, let's say 1 cup of oil, and I were to add the same amount of energy as here 1 cup of water, the oil will rise to a higher temperature if I give the same amount of energy than if I give the energy to the water. And that's because there's really only one thing in the oil that can absorb the energy, and that's the molecules themselves moving around faster. Whereas I give the energy to water, there are two things that can absorb the energy. There's the water molecule itself, they'll move around faster, that will elevate the temperature of the water. But the hydrogen bonds can also absorb the energy that will break the hydrogen bond, but it will not increase the temperature. Any question about that? And then when you break the hydrogen bonds of the water molecule that has the most energy will be the one with the hydrogen bonds broken. And what's that going to do? That water molecule is going to leave the water, go into the air, and that will keep the water cooler because the hottest water molecule is the one leaving the water. Any question about that? So when the hottest water molecule is leaving, we call that water evaporating, and that will take the heat away with it. That's actually very important for people in organisms. They use water's evaporation to keep themselves cool, and we call that perspiration. Any question about any of that? All right. Water can split apart, meaning a water molecule on the planet Earth can split into hydrogen plus ion and an OH minus ion. This is on the surface of the planet Earth without any electricity going through the system. You do not get water splitting into hydrogen and oxygen, meaning 2 hydrogens plus 1 and 1 oxygen minus 2. You don't get that happening on the surface of the Earth. You get it happening on the surface of the sun, because the sun is much hotter than the Earth. But on the surface of the Earth, water only splits into H plus and OH minus. The H plus is a proton. The OH minus, we're going to call it a hydroxide ion. Anything with a positive 1 or a negative 1 or a positive 2 or a negative 2 or some positive multiplier of that, we call ions. So it's not a positive, partial positive charge on that hydrogen. It's a +1 charge. And the reason why it's a +1 is the electron leaves the hydrogen and goes to the OH group, and that's why it's a -1 charge. These charged molecules can participate in chemical reactions, and they give rise to the pH of water. Any question about any of that? All right, let's talk a little bit more about pH. Here we're looking at a pH scale. Neutral water has the concentration of H plus ions in solution equal to the concentration of the OH ions in solution. So when you have water breaking apart, it'll make 1 H plus and 1 OH negative, and that'll be pure water with a pH of 7. However, you can get increasing acidity, such as urine, slightly acidic, wine and tomato juice around pH 4, grapefruit juice even more acidic, pH 3, lemon juice more acidic, pH 2, stomach acid around pH 1.5. And then the most acidic thing that I know of is the acid in your car batteries, someplace around pH 1 to pH 0. That is increasing acidity. Now, on the other side, you can have increasing basicity or alkalinity, where the pH will be higher than 7. Seawater above pH 8, I think it's pH 8.4, maybe 8.3 or 8.5, something like that. Milk of magnesia something close to pH 10.5. Household ammonia around pH 11.5. Household bleach around pH 12.5. And then the most acidic or basic or alkaline thing you know of is the oven cleaner, what you spray in your ovens to clean it, and that'll be around pH 13.5. Lime water is something that's even more alkaline, pH 14. Now at pH 14, all of the H plus in water is gone, and all you have left is OH minus. And the same thing at pH 0, all you have left here is H plus in solution, all of the OH minus is gone. So the pH scale is the concentration of H plus ions in solution. The more H plus you have in solution, the more acidic the solution will be. The fewer H plus ions you have in solution, the more basic it will be. Any question about that? And the pH scale always ranges from 0, meaning there's no OH minus in solution, it's only H plus in solution, to pH 14, where there's only OH minus in solution. There's no H plus in solution. Any question about any of that? All right, let's talk a little bit more about the pH. The pH scale ranges from 0 to 14. It is a log scale. A log scale means that when you go from one number to the next, like pH 7 to pH 6, you're increasing the H plus concentration by tenfold. That's why it's a log scale. So when you go from pH 6 to 5, you increase the H plus tenfold, or that would be 100-fold from pH 7. Acid solutions are when the H plus ions in solution are greater than the OH minus. Basic or alkaline solutions are when the OH minus in solution is greater than the H plus in solution. Most organisms grow best between a pH of 6 to 8, meaning around pH 7. Most organisms grow best around pH 7. And the pH is the amount of the H plus ions in solution. Specifically, the pH is equal to the negative log of the concentration of the H plus ions in solution. Let me end the show here. Open up a new book here. When we're talking about pH equal to 7, what we have is one water molecule splitting into H plus and OH minus per 1 times 10 to the 7th water molecules. Don't know what that other part is. So let me get that superscript. Oop. And that should be a superscript as well. Any question about that? So at pH 7, we have one water molecule splitting into H plus ion and OH minus per 1 times 10 to the 7th water molecules. What do you have at pH 6? Oops, got a break there. You have one water molecule splitting to H plus and OH minus per 1 times 10 to the 6 water molecules. Any question about that? See if I can get the thing there. What do you have for pH 5? I didn't get it.
Yeah, one water molecule splitting into OH, it's splitting into H plus and OH,
Minus
yeah, OH minus,
per.
per 1 times 10 to the fifth.
Yep. And the same thing with pH 8. Let me go ahead and see if I can get this. There, I got it, I think.
When you were talking about how the temperature of water and how it
Mhm.
has to do with the vibration of the water molecules.
Uh-huh.
If I were to answer that question on the worksheet discussion post, in chemistry they call that kinetic energy. Could I answer it using that term kinetic energy
You
or
could say the kinetic energy of the water molecules. Yes. I'm
okay,
not using that term, but you can.
okay.
Yeah. All right. So if pH 8, you got one water molecule splitting to H plus ion and OH minus per 1 times 10 to the 8th water molecules, meaning there's less H plus in solution. Any question about any of that? And that's literally what the pH means. Which is actually the negative of the log of the H plus ion concentration. But you don't need to know that. All right, let's come back here. Oh, I've already talked about that. So let's move on. An acid is a substance that dissociates, giving up one or more H plus ions in solution. Like HCl, you dissolve HCl in water. HCl will dissociate into H plus ions and chloride minus ions, making more H plus in solution. And that is why HCl is an acid. Any question about any of that? Now, your textbook says a base is a substance that dissociates, giving up OH minus in solution. Like, for example, sodium hydroxide, you dissolve that in water. Sodium hydroxide can break into sodium ions, +1, and OH minus, -1. And that'll increase the OH minus in solution. And that's why sodium hydroxide is a base, because there will be more OH minus in solution when you add sodium hydroxide. And sodium hydroxide is a base. However, if you were to put bicarbonate, like sodium bicarbonate, which is baking soda, in water, the bicarbonate will absorb the H plus and form carbonic acid, H2CO3. That will reduce the H plus ions in solution. And so bicarbonate, or sodium bicarbonate, is a base, not because it will give up OH minus, but because it will absorb the H plus ions in solution. And a base is something that either gives off OH minus in solution or something that absorbs H plus in solution. And you're only going to get this from me because, like I said, your textbook doesn't state this part of a base. Don't know why, but it doesn't. And that's why sodium bicarbonate or baking soda is a base, because it absorbs H plus in solution. This actually is an important buffer in your body. We have buffers in our body to keep our pH stable, meaning around pH 7, and when you breathe, or breathe out, you're breathing out CO2. That CO2 can be absorbed in water or your blood. And let me end the show and show it here. Up. So CO2, I'm just going to write it that way because CO2 can be absorbed by water or the water in your blood. Oops, I should actually add that, sorry. So you have to have it together to form H2CO3. And that really should be in subscripts here. Let me put that in there. The same with that. I'm not getting that second one to work, so let's get rid of it. That can break apart into H plus and we'll just say and H. Let's go ahead and get that. Up. CO3. And this will have a negative charge. There we go. Let's blow that up so you can see it. And this is an important buffer, this one and that one. And then that would release H plus to make your blood more acidic if it's needed. And then this arrow can go the other way as well. Well, sort of. Nope. Yeah, I can't get it to go. Oh well, did my best. The arrow can go the other way. Maybe I can put in an arrow. Not sure where that would be. Let's see it. It's not adding it for some reason. All right. See if I can reverse that. I might not be able to. Well, any questions? Because I'm not finding how to do this very easy. That should be going the other way. Oh, there we go. You needed two. So this can go the other way, and that will remove hydrogen ions from solution to make the blood more basic. So that these two molecules are important buffers in the blood. And if you really needed it, this can break apart into something else. So that can break apart into this again. Oop. Well, I don't have the arrow, but close enough. And that will be off. And then that will be a -2. Let's see if I can get this all on one page. There we go. And that will make this actually 2 of these. If you needed more hydrogen ions in solution, this can break apart. However, this would only happen at when the blood is fairly alkaline, and so that would kill the patient. So this doesn't normally happen in the human body where this breaks down into that. Any question about any of that? Not sure where that 2 came from. All right. A salt is a substance that dissociates into a cation. Something has a positive charge, and that's a complete charge, and an anion, something that has a negative charge, and that's a complete -1 or -2 charge, neither of which are H plus or OH minus. Sodium chloride is a salt, table salt, and it can break into sodium ions and chloride. But so is magnesium chloride. It is a salt because it'll break down into magnesium plus 2 of them, I think. No, 1 of them plus 2, and then 2 chloride ions, -1. So sodium chloride is a salt, but so is magnesium chloride, and any substance that breaks into a cation and an anion we call a salt. This is what a chemist calls a salt. Any question about that? If it breaks into H plus or OH minus, we don't call it a salt, because if it breaks into H plus, we call it an acid, and if it breaks into OH minus, we call it a base. Electrolytes are substances that dissociate into ions in solution, and then they can conduct electricity. Like sodium chloride dissociates into the ion, sodium and chloride ion. And so table salt, sodium chloride, is an electrolyte because it can conduct electricity. Salt water can conduct electricity much more readily than pure water. Any question about any of that? And that's why, if you haven't heard, you should not swim in the ocean or even be in the ocean during an electrical storm, because if lightning hits anywhere close to you, the lightning strike can be conducted by the salt water to your body, and then you'll be electrocuted. Whereas if you're swimming in a lake or a pond, if the lightning gets close to you, it would have to be really, really close before it would conduct electricity to your body. So we're talking about within a few feet of your body. If it's on the other side of the lake or the other side of the river, it's not going to electrocute you. But if you're swimming in salt water and the lightning hits even fairly far away, you could be getting the electric from the conductivity of the salt water. Any question about any of that? All right. That's enough about salts and pH and electrolytes. Let's move back to organic compounds. Here you're seeing some organic compounds. The simplest one is really acetic acid. Here's a more normal organic compound right here. I guess that's really the simplest organic compound right here, but these are organic compounds. You can draw them in the stick figure like this, or the ring structure like that. If you're drawing it in the ring structure, wherever there's a point, you have a carbon. So right there, there's a point and there's a carbon there. At each point, there's a carbon. If there's not a carbon at this place, You have to write in what the element is. Any question about any of that? You don't need to memorize any of these. I'm just showing you some different organic compounds. They all have carbon and hydrogen in them. The simplest organic compounds are called hydrocarbons, and all they are composed of is carbon and hydrogen. So these right here and these right here are hydrocarbons. These might be hydrocarbons. I can't see what they are, but organic compounds can have other molecules in them. Like frequently, they can have oxygen in them. Let me blow this up again. Like acetic acid has some oxygen in it, and phospholipid has some oxygen in it, right there and there. When we're looking at the phospholipid, you'll note that most of the atoms are held together by the carbon-carbon bonding. So all of this right here is held together by the carbon-carbon bonding. Same with this one here, and then this one here. The only place where there's in this molecule where the molecule is held together not by a carbon-carbon bond is right here, where the oxygen is actually holding the two carbons together, and then right there and right there. So in organic compounds, usually, at least most, if not all of the molecule is held together by the carbon bonding. Any question about any of that? All right, organic compounds always contain hydrogen and carbon. Like I said, the simplest organic compounds are called hydrocarbons, and all they have are carbon and hydrogen. But they may contain other elements, such as oxygen. They may contain other elements like nitrogen, sulfur, phosphorus. All of them are held together by covalent chemical bonds, usually covalent chemical bond with carbon. Not always, but most of them are with carbon. But they're all held together by a chemical covalent bond. Compared to inorganic molecules, organic molecules are more complex. Showing you here, all of these molecules and these molecules, and actually all of these molecules too, are more complex than an inorganic compound. You have to get really small, like this one, maybe even that one, before you get an organic compound which is similar to an inorganic compound. Organic compounds are capable of more complicated biological functions. And as I stated, here's some examples of organic compounds. Some other organic compounds that you know of are fats, lipids, carbohydrates, and proteins. I guess the fourth, I said fats and lipids, that's not four. That's actually the same, fat and lipid. So the fourth would be a nucleic acid, sorry. Organic compounds are often held together with carbon because carbon can hold four other atoms, can chemically combine with another atom in four of them. Like there, this carbon is bound to four other atoms with a chemical covalent bond. And you often find the carbons in a chain or a ring structure, this being a chain of carbons, and there's the ring structure of carbons. The carbon skeleton backbone is the chain of carbons in the molecule, the organic molecule, holding the molecule together. Like here, the carbon skeleton or the backbone is this CCC bond, which holds all the other atoms together. Any question about that? And it's usually the carbon skeleton backbone holding the molecule together. But like I stated, there are some exceptions. Like right there, oxygen is part of the backbone holding the molecule together. But most of the backbone is from carbon-carbon bonds, all of that. You can have functional groups bound to the organic compound. A functional group influences the chemical behavior of the organic compound. For example, OH is a functional group, and you attach it to methanol, this one right here, methane, I guess, not methanol. Methanol is what I was talking about. It gives the molecule different chemical properties when you attach OH to it than methane has. For example, methane is a nonpolar molecule. Methanol containing the OH group is a polar molecule because this OH group is polar. Methane does not dissolve in water, but methanol does. So this functional group is giving this molecule different properties. And the functional groups are important in the organic compound because they give the molecule different properties. Any question about any of that? So the functional groups are responsible for most of the chemical and physical properties of a particular organic compound or an organic molecule. The hydroxyl group in alcohols are hydrophilic, and so an alcohol can dissolve in water as well as dissolving in a lipid like oil or alcohol. And so that functional group OH helps dissolve the alcohol in water. Methane itself can dissolve in a fat or a lipid like oil, like olive oil, I guess. Any question about any of that? All right, here are the functional groups surrounded in the red box you need to know. OH, found in lipids, carbohydrates, nucleic acids, which isn't stated here. You need to know the amino group, the NH2 group, found in proteins and amino acids. You need to know the carboxyl group, COO, meaning 2O, and then an H. This is found in lipids, proteins, organic acids, even amino acids. And then the phosphate group, the PO4 negative group. Phosphate groups are found in ATP and DNA, as well as in phospholipids. I think we talked about phospholipids. If we haven't, we will. Why do you think I want you to know the functional groups I've mentioned? And I don't want you to know necessarily like a ketone or the methyl group. Anyone have a guess? It has to do where you find these molecules or these functional groups.
Because you find them in microorganisms.
Yeah, you find these functional groups in the 4 biological molecules, which you find obviously in living organisms. Frequently, you can find more than one functional group in a single molecule, like an amino acid has both the amino group and the carboxyl group in that one amino acid. The R is a acronym or shorthand for saying the rest of the molecule is here, and the R can be essentially anything. Any question about any of that? Like in a protein, you get amino groups, carboxyl groups, you get hydroxyl groups. In ATP, you get hydroxyl groups, phosphate groups. I'm not sure if you get amino groups or not. Let me think about that in ATP. Yeah, there's a few amino groups in ATP as well. Not many, but there's a few. All right. Organic compounds typically are made up of small organic molecules which combine into the macromolecule, meaning you have a large molecule that can be made up of smaller parts or units. We can even call them smaller molecules. And so we say macromolecules are often made up of polymers, consisting of many small repeating molecules, and we call the small molecules monomers. So a polymer is a large molecule made up of many monomers. Like starch is a macromolecule that we can call a polymer, and it is made up of many monomers, which are all glucose. And what you do for starch is you just hook the glucose together one after the other, and you no longer have glucose anymore, you have starch, which is a polymer of glucose. So the monomer of starch is glucose. Any question about any of that? Let's see if I can finish this. You can have the monomers come together to form a dimer, would really be it if this is a one monomer and that's one monomer. But here it's calling it a polymer. And what you do is you take off the OH of one monomer and the H of another monomer to form water. And then this R here can directly bind to that R there, creating the dimer. And this happens in dehydration synthesis, also called condensation reaction, when you're going this way, forming water. That always makes a larger molecule. The smaller molecules combine to make a larger molecule. And then you can take the larger molecule and add water, and that's called hydrolysis, splitting the larger molecule with water to form, in this case, a dimer forming two monomers. So hydrolysis is the reverse of dehydration synthesis. And you should remember what hydrolysis is, because if you remember, Marty McFly in Back to the Future 2 said, "Ma, you sure know how to hydrate a pizza," when she took this hockey puck, put it in her hydrolysis machine, and out came this beautiful looking pizza. Marty McFly's mother, don't remember her name, Mrs. McFly, was hydrating the pizza by under hydrolysis, adding the water to it to form the monomers to make the pizza. Any question about any of that? All right, I think I'll stop here and we'll continue with this next time. Any questions? All right, if there's no questions, I'll see you at 6:30 for the lab.